Welcome to another new video. In today's video, I'm going to be showing you the fluorescent inverter which I've made. So here is the main inductor, and here is the second inductor used in some filterings, and here's the fluorescent tube. And it provides a DC voltage about 12 volts, and it needs a little bit of coupling. Here you can see this lights up alright. And the functionality of the circuit is pretty simple, as we can see here. It basically involves two transistors, a ferrite toroid or iron core toroid, two resistors, and a main inductor, a resonance cap, and a current limiting capacitor, which used in limiting the currents to power the fluorescent lamps. And fluorescent lamp is worked by connecting both filament ends together. So like cold cathode operations, but here is in hot cathode, since when the currents flow through it, the electrode will get heated. Here's a second bit of clip of this little inverter driving a bit more powerful bulb here. So we can see the 18 watts bulb does get light up pretty well, but not at its full brightness, since will require a bit more input voltage. This just shows the inverter it does works with varied amounts of voltage and different type of lamp, since the main thing balancing the entire current is through the C2 capacitor. So here is the circuit that works with the fluorescent lamp. So here is a Royer-Baxandall oscillator or Royer-Baxandall converter. In this circuit, I've shown you the PNP version with two transistors. Here I've done a little bit of circuit diagram, and then just shall go into a bit of detail of how the circuits work. Previously I've done some dual sleeve circuit because I explained everything so simply that a lot of details just get excluded. But this time, I will explain a little bit further about how the circuits work. This circuit, unlike a blocking oscillator, it has much higher switching efficiencies. It's a bit different to the original Royer oscillator, since the inclusion of L1 and C1 makes the circuit much more efficient, except C1 sometimes does increase or sometimes decrease the efficiency, whereas L1 always improves the efficiency if you use the right kind of inductor. So goes a little bit of detail of how the circuits work, if we can ignore L1 just yet. So first, the currents pass through everything including L1, and those two coils here is being controlled by two transistors, Q1 and Q2. Q1 and Q2, when they start off with, is not conductive, but they've been powered by the two resistors here, R1 and R2. One of the transistors or one of the resistors will have a lower value, or the transistor have a higher gain than the other one. So current will flow a bit more in the first transistor or the second one. So we just say the first transistor actually switch on first. It has the most power being given to it by the feedback coil. How does it work? So first, the voltage flow through the center tap of the main inductor, so which is the primary side of the coil. When voltage flow through the sides, the dot itself will become negative. So if we can see here, on the feedback, the dot is given to the Q2. Q2 is being pulled down to its minimum, so it no longer turns on anymore. And at the same time, the feedback will also connect it to the transistor. This caused the transistor to switch on even further until two things happen. Either the transistor is fully saturated, no more currents can flow through more, or either the entire inductor is being saturated and the electrical characteristic changes as well. And this is really important for T1. It's a air-cooled gap, unless you have a really large ferrite allows all the field to stays in. If not, the ferrite has really high loss when it gets saturated, as the magnetic field leaks everywhere and produce a lot of interference. But any case, either Q1 saturates or the inductor saturates. When it does get saturated, no more magnetic field gets stuck into the core. As so in the same time, so because no more change in magnetic field, the feedback coil can no longer keep on producing its voltage, so which caused the voltage here to collapse. With less voltage, the transistor starts to switch off. As it starts to switch off, the inductor here opposes any change. When it does oppose any change, here will be pulling down even lower. As voltage stops being provided, the field itself collapses down. This causes the feedback to change its polarity. When it does, Q1 now will be completely turned off, as here becomes negative, here becomes positive, which will latch Q2 on straight away. When it does, the current will flow through Q2 and the cycle shall repeat as the same here. So all the power will flow through Q2 now. As it does flow through Q2, the dots itself now becomes the positive, as we can see of the winding polarities, so which turns Q2 on even further until either Q2 got saturated or either the transformer gets saturated. No more change in magnetic field flux occurs in the core. So at that point, no more voltage is being induced. The voltage starts to collapse down on the feedback, which does switch the Q2 off really quickly and turn on Q1. Here is the capacitor in the circuit, which shall follow the LC resonance circuit equation. The fun thing is that the change in the voltage around here, the terminals, it does affect the overall resonant frequency by a bit. Not too much, it does affect. As well as this L1 included, it does have some roles in the circuit, which I shall go into some details. In the original Royer oscillator, L1 is not included. But what it happens is that when it switch on transistor and switch off, cross conduction may happen since the transistor cannot turn off that fast, so both transistors will remain turned on at the same time. When that does happen, you basically got yourself a short circuit. All the currents will flow through. But as for an inductor, it has a really good properties if you learn electronics. Inductor opposes any change in its current, so that at that exact moment, the inductor itself will have a really high resistance. So at that point, the current flow through isn't that much at all, so the transistor is being prevented from further heating, and efficiency of this switching circuit improves drastically. At the same time, when it's back to its regular operation, as it followed the second half of the cycle of its oscillations, but the inductor itself already has some more original currents being pushed through the entire circuit. So that point on, inductor opposes any change of decreasing currents by pushing more voltage through the entire circuit, which allows a higher voltage to be reached for C22 in order to work, because the higher the voltage around the primary will induce the higher the voltage on the secondary. Here I've drawn a little bit more about like an NPN transistor, how it works. If we remove that side, the transistor itself will turn off, as the load shall receive no power, because it's just an open switch. But when we just apply a little bit of voltage with the current limiting resistor to the base of the NPN transistor, this allows the entire transistor to turn on, which allows a way greater amount of current to be fed through, which is called amplifications. So at that case, so the transistor actually amplifies the signal being fed through the power supply in order to switch the transformer itself. One more tip, I haven't released any components values, for example R1, R2 or C1 or C2 etc. is because different size of ferrite cores can result in different numbers of turns, and those have different components values, which It basically lets you to explore yourself the best components values that works for you with the highest efficiency you should find out, as well as L1. Usually greater than 100 microfarad should work well, but it can be a bit higher. And here some people operate with a filtering capacitor. In my case, I just remove it. Since this circuit just switched so cleanly, it doesn't produce much interference. And now, the main purpose here, which I explore. C2 is a really interesting capacitor, since in an AC circuit, capacitor has its own impedance. When it does flow through the AC currents, it actually acts like a resistor here. I didn't choose the capacitor to be in resonance with the inductor here, the secondary. If it's in resonance, in theory I'll be able to switch on a much powerful fluorescent lamp. When it's in resonance, the total amount of voltage induced across the capacitor can be really large, which I could improve here, which that step I shall find out in the future. But anyway, we included a C2. Actually, it limits the current acting like a resistor have a certain resistance value in an AC circuit with a given frequency. But at the same time, it didn't heat up. You would think, where did energy go? All the energy is fed right back into the system, which causes it to have really high efficiencies. As we can see, capacitor or inductor, they shall have the same properties of impedance, which have changing their resistance value depends on their frequencies. In some older traditional fluorescent fittings, they have a ballast. Ballast is just a wine-coiled inductor, which has pretty high inductance. That case with 50 Hz, it does work, but on the waveform, when it's falling back down, the inductor resists any change. At that moment, it acts like a generator, but at the same time, it gives a really poor power factor to the entire circuit system, but it will be limited since we're working with DC here. With the power factor in the AC circuits you have to consider, because during the certain moment of the sine wave, it requires much higher currents than usual, but at the same time, it also at certain part, it doesn't require much current at all. And sometimes you just feed the currents back into the system, which can create some problem for some resistance loss in some regular material. The fluorescent lamp, both electrode is being shorted, work in the cold cathode emission system, whereas in the first startup, the filament is all cold. It just works by pure ionization of the panning gas mixture. The panning gas have a really low striking voltage, which allows the mixture to turn on. Once it turns on, all the currents will be hitting both electrodes equally, which creates thermionic emission of electron cloud just around the filaments. So when the gas ionizes, it tries to strike the filament material. It just can't strike anymore since of the electron cloud zone around the filaments when it gets heated. Here's some values of transistor. It works pretty well. It just depends on the voltage you're gonna feed it through. If you're gonna feed through some higher voltage, I recommend you with a transistor that has slightly lower current ratings but have a high voltage rating. If you want to work with lower voltage, then you need one have a higher current ratings. This circuit can also work at the same time with the PNP transistor. Everything is just get reversed, as you can see the PNP amplification by feeding a negative signal through the base. PNP works the same way as NPN, you just have to reverse it, but PNP is rarer to find in electronics since it's used a bit less compared to NPN. In the same way, all the resistors and capacitor values can stay the same. One interesting factor that R1 and R2, you have to find out yourself. Different transistors have different amplification factors. You may also want to change the feedback winding lower or higher, depends how much you want to switch the transistor on. The lower the R1 and R2, the value, the more power you can feed through the system, but at the same time to sacrifice the efficiency of overall switching. Main thing you should consider is changing the feedback winding, you can vary it between 2 turns to 7 turns. Doesn't suggest you go any higher, just in case if you're overvolting the transistor. You can also add voltage protecting diodes through the transistor, but in this circuit it doesn't matter much since the switching is really clean and doesn't have any voltage spikes through the entire system. Only current spike, which has been limited by this L1. And that's it for this video, and thanks for watching. See you next time.